Okay, sorry for the delay. It seems to work now. Yeah, today we're talking about Gaussian processes. And we have, last week we had already a first glimpse into this topic. And today we'll have it in more detail. I think Gaussian processes are a very important topic in machine learning, a very new and modern topic. Many people nowadays use Gaussian processes. And in particular, they can be used for two kinds of different problems. One's for regression and one for classification. And we'll have this in the 2 hours we did today. We will have, in the first hour, we'll have only regression. And in the second one, we'll have classification. First, we start with the motivation. So far, we have had techniques that learn a parametric representation of a function, right? We have regression. We had a linear regression model, for example. And what we wanted to do there is we wanted to learn parameters of a given function in a best way. So we have some kind of error function that we optimize, and we have some training data, and this is the basic technique that we usually do. However, very often it's very hard to find such a parametric model, right? We'd like to do that. We have to specify a function that kind of reflects our mapping between data and semantics, whatever we would like to add to it. And very often this is very hard to find such a function, right? Because, of course, the kind of function we choose defines a lot on how well we actually can map our data to our semantics. And the Gaussian processes, they try to do this not with a parametric formulation, but implicitly. So they try to model these functions data-driven, right? By given data, you can then compute function values for every new data point, but you can never really write down the function itself, right? This has a lot of advantages. It also has disadvantages. So there's always a trade-off. But in general, the motivation of this is that it's a much more general approach, right? It's just much more general way of learning models into data. So the whole idea is that we represent the data using a large multivariate normal distribution, a Gaussian, where every data point in a training data is one variable in that very high, large variate normal distribution, right? So if you have many data points, of course, then you have a very large Gaussian distribution with a big covariance matrix, which of course makes the problem with computation-wise, but it gives you also very good power, because then you can really understand the statistical relationships between data points, right? It actually looks at how strong are data points correlated with each other, and this correlation is reflected in the covariance matrix. And the only requirement that we say here is we assume that any given subset of our data is assumed to be a joint normal distribution, which is kind of an intuitive way, right? If we can't assume anything, then assuming things are Gaussian is not a bad thing to do, right? We know that because most processes in the natural world are Gaussian distributed. So that means if you assume that subsets of data points are joint in normal distribution, I think this is not a bad assumption. Now, before we start, we need a little bit of formulations, mathematical-wise, and I'm doing this again here on the board, and then we'll later see how we use these formulate these equations here. So the first thing we start asking ourselves is, what is the inverse of such a matrix? Which comes a bit out of the blue. What does this have to do with the Gaussian process? We'll see this later. We have a block matrix A, B, C, D, and what we like to do is we would like to invert that matrix. So, and we will see that there is a nice way of doing that, right? How do you compute that? And the way, by doing that, we'll see some kind of formula that we'll later use in our derivation, right? So they just come out of the derivation from this inverse here. The basic motivation for that is that we'll later have Gaussians where we need to condition on a subset of variables on that Gaussian. And conditioning can be expressed in a block matrix like this, where your covariance matrix is a block matrix, and you have to invert that block matrix, and there's a very closed form, a nice way of expressing that conditional probability. So now, to start, we first describe. We first say so the first idea to do that is to convert this matrix into a diagonal form, and this can be done easily with one possible way. There's two possible ways. The first one we start now. First, we pre-multiply this matrix with another matrix that is upper triangular, and here on this, here we need to say b minus b times d inverse. Why is that? Because if we now multiply this with this matrix here, right, then we'll have b times I plus d times b d to the minus 1, which is again b, right? And then this gives 0. This is the first idea, right? The rest is just 1, right? So this is the first thing we can do, right? If we do this, then we get a matrix, something like this here. This is A, this stays the same, this is 0, this is 0, this is C, and now here we have D. Sorry, this is not correct. Yes, this is A minus B d to the minus 1 C. Right? Yeah. And here we have our 0. And this is B is 0, D times 1 is D. Right? So we already got rid of one thing, which is the 0 here. And now we can multiply this matrix from the right with another with a lower triangular matrix, do the same trick again, right? Now we simply have to do a slightly different thing. Now we have to do times minus d to the minus 1 C, right? So this is the same idea. We'd like to get rid of the C here to make this matrix A minus B d to the minus 1 C 0 C D, right? This gives. We have the same here. We copy that. A to the minus A minus B d to the minus 1 C. This is 0. This is 0. This is C. This is D times d to the minus 1 times C. So this is again 0. And this is 0. And this is D. Is that correct? Yes. Now, this expression is a very common expression. It happens a lot in many things. We call this a sure complement, right? So we say this is a sure complement of a matrix M. This is our matrix M of M with respect to D, right? Why is this M with respect to D? Well, we look at D. The rule to compute the sure complement is always go to the opposite of your D and then go around. A minus B times D to the inverse times C. Right? This is the definition of the sure complement. And we'll see later that this is important. Now what we can do is we have this matrix times this matrix gives this one over there. We call this matrix X. We call this matrix already M, right? This is our M matrix. We have multiplied with this value here, which is Z. and we can compute and can name this matrix as W. So we have equation now that says X times M times Z equals W. Now, to invert all that, we just invert on both sides, right? Which is the same as, now we have to also change the order. This is the rule of inversion. Of course, we assume that all these matrices are invertible, but that's no problem, because this is lower triangle, upper triangular, this is lower triangular, these are invertible. We assume that M is anyhow invertible, right? This equals W to the minus 1. And now we simply multiply from the left with Z and from the right with X. So we have M minus 1 equals Z times W to the minus 1 times X. Right? Now we have our formulation for the inverse. Right? And now we simply plug this in again, what we have, right? We say this is the same as Z, which is our matrix, our triangular matrix here, I0 minus D to the minus 1 CI times our diagonal matrix. This is the Schur complement. And of course, now what we have to do is we have to invert W, right? And inverting a diagonal matrix is no problem at all, because we just invert every diagonal entry. Right? We invert that thing, we invert that thing, and we have to still use X, which is here, right? Minus B D to the minus 1. Right? This is our expression now for the inverse of M. And now we just multiply that, right? Which is the same as we have the Schur complement, just stays the same, right? We have this is 0, this is 0. This is the Schur complement, the inverse of the Schur complement actually, right? First. The order is always important of the matrices, right? It's always very important. So what we can do is we say this is minus D to the minus 1 C of Schur complement, right? Times 0, and here we have 0, and here's D to the minus 1 again, times this thing here. Which is the same as, this is Schur complement, this is Schur complement times B D to the minus 1, this is minus D to the 1 C Schur complement. And here, and now this is interesting here, now we have the biggest term here in the lower right corner. So that means we have to multiply this with this plus this. So I do the opposite order. I start with the first one. I say this is D to the minus 1 plus, I have a minus sign here gives plus D to the minus 1 C M Schur complement minus 1 times B D to the minus 1, right? So this is the largest expression that we have here. All the rest is quite easy, I think. So that means if we have the Schur complement already done, then we can directly invert that matrix, right? We just plug the Schur complement. It appears now in 4 times here, right? And all the rest is easy because D, we assume that D is easy to compute, D to the minus 1, so they can then directly invert this matrix, right?
There's a minus missing.
A minus where? Where? Sorry. Yes, that's right. Yeah. So this is our expression. I think I have this already in the in the last. Well, I'm not showing this now. Just give me one more thing I would like to show you. The trick is what we can now do is this thing that what we did here is we pre-multiplied with the lower triangular matrix. We could have done the same by pre-multiplying with the lower triangular matrix. The only thing that it would change then is instead of using this, B D to the minus 1, we then use minus D to the minus 1 minus a to the minus 1 c, right? So we could have multiplied, instead of this matrix, we could have used this matrix here. Minus a to the minus 1 c, right? It's the same idea. And on the right side, we could have done the same thing with the opposite of that, right? We would then have this matrix here. Minus c, a to the minus 1, 0, I. So these two matrices, they do the same job, right? Which is nice, right? But then we would have a different Schur complement. We would then have the Schur complement m with respect to a. And we would have, of course, the Schur complement on the other side, right? It would simply switch around. So that would be a here, and this would be the Schur complement m given a, m with respect to a. Which then means we would then have the same expression here, just with, we would then have a to the minus 1 plus a minus 1 c. No, sorry. This is c. Give me a second. Oh, yeah. This should be c. B a to the minus 1. I'm not perfectly sure if this is correct, but it should be correct, let's say. And importantly is that on the lower right, we would then have this one here, we would then have m, the Schur complement of m with respect to a, and the inverse of it, right? And of course, these terms are very similar. I'm not writing these terms right now. This is just for you to understand that there's two ways of doing that. And by doing these two ways, we can now directly prove the matrix inversion lemma that we had last week. This was the matrix inversion lemma, which is nothing else than the inverse of the Schur complement. The slight difference is that we don't have C inverse here. Okay, that's not a big problem. We can say C, we can have another C, which is the inverse of this C, right? So this is no problem. But what we do is now we equate this with this by equating each term, each thing. Right? This is the Schur complement with respect to D, right? And this equals this one here. And you see, this is exactly the topic here. The minus sign. I'm just looking for the minus sign. That I don't know at the moment. There must be a plus sign there. This is confusing at the moment, but yeah. I can't explain this at the moment why this is. Because in the book it's written with a plus. No, sorry. Of course. Yeah, the minus sign here. So the Schur complement has a minus sign here, right? So you would have to imagine that this matrix is you had a minus sign in the C matrix, or in the B matrix, for example, and then you would have a plus sign here, right? So this switches things around, right? So the Schur complement is defined with a minus sign in here, right? And that makes this a plus sign. That's the difference. But this is the same as this, right? This is the matrix inversion lemma. Okay. So far, the math. We'll come back to this in a minute. One nice thing, of course, what we already saw last week, we can now use the matrix inversion lemma to compute this thing here, right? So what we did is we have our solution to our kernelized regression vector. So this W vector is the solution to our regression. And now using the matrix inversion lemma, we saw this last week, we can now turn things around. Now instead of having a matrix in the feature space, we have a matrix in the space of data points, right? N is the number of data points, and D is the number of features in the space. So we have just this exactly the same expression. This is just turning things around. The trick there is now that we can now express this matrix with a kernel, right? This is our kernel matrix. We plug this in, And the solution of that is this matrix here, right? This vector here. A is our kernel matrix plus our prior here. This comes from the prior, right? Our regularizer. We invert that and we multiply with t, where t is our given output data from the training set, right? And then if we plug this in, then we can get this as a prediction, right? For a new point x here, if you want to do a prediction, then we just plug this in here, this a thing in our formulation, right? We just say we express w by a, and this is then our equation that we get, right? So what we have to do is we have to compute this thing here, which is for a new x, we compute the kernel to all training data, right? This vector is as long as we have training data points, which means that we just compare our x with all the given training data. And then this is a simple dot product, right? We have a matrix times another vector here, so this whole thing is another vector. But all this information is given from the training data. We know t, and we know k, we know everything. So we can pre-compute this whole thing, and then for inference, for prediction, the only thing we do is do the dot product of this thing with the other vector, right? This is prediction with our regression model. And now we just try to express that in a more general way using Gaussian processes. Right? The Gaussian process is basically a general description of exactly that. This is the formulation for the Gaussian process prediction. And of course, what we can also do now is, instead of having a most likely prediction, we can now also add uncertainty. We can also now estimate a covariance matrix of our prediction, right? And we'll see in a minute how this works. Before that, what I promised already, we will have to look into Gaussian marginals and Gaussian conditionals. This is just a way of writing it. So assume we have two variables, right, xa and xb, and they're jointly Gaussian. This is the assumption of the Gaussian process, that we have a number of variables that are jointly Gaussian. That means I can write them in a big long vector with a big mu vector, a mean vector, and a big covariance matrix. Covariance matrices are, of course, symmetric. That means this upper part is just the transpose of the lower left part, right? And sigma AA and sigma BB are, again, symmetric. And now the question is, how can we compute this thing here? And this comes directly from the formulation that we had here, right? What we can do now is we can, let me just remove this here, write this as a big Gaussian. So we say the joint of XA and XB is, and I'm not writing the normalizer, this is just I'm only writing the exponential of 1/2 over, and then now we have this big Gaussian this with XA minus mu A, XB minus mu B times our matrix, which is sigma AA, sigma AB, sigma BA, sigma BB, inverse, right? Times, of course we have to transpose this first, XA minus mu A, XB minus mu B, right? This is the general expression for Gaussian, for multivariate Gaussian, right? And for the moment we can assume that these are just one variable, right? One variable x and one xa and one variable xb. So we have two variables here and they're jointly Gaussian. And now we just use our formulation. Now we invert that thing with our formula that we have here by simply plugging in this formula here in the inverse, right? This is the same as, and I'm not doing all the steps, but I'm giving you the idea, right? XB minus mu B transpose, and now we have again our matrices Z and X. We simply plug in Z, which is here this, right? We have a lower triangular matrix here, and now we have to plug in D to -1 this is Z sigma BB, to the minus 1 times C, which is sigma BA. And we have our diagonal matrix here, right? This is the Schur complement of sigma with respect to sigma BB to the minus 1. This is diagonal. And here we have just sigma BB to the minus 1. And the same here, right? Now we have to do, this is a upper triangular matrix here now, simply with things turned around. So here we have minus sigma AB times sigma BB to the minus 1. And of course we have to now also post-multiply this whole thing with our XA minus mu A, XB minus mu B. Right? It's a long, long thing. But basically what this simply means is we have x minus mu times covariance matrix inverse times, again, x minus mu, right? This is just the expression of the Gaussian, nothing else. And now what we can do is we can now multiply this thing here, which then gives us a long row vector, right? And the trick then is times mu A t minus xb minus mu b transpose times sigma bb minus 1 sigma ba, right? Yes, this is the one thing, and the other thing is just xb minus mu b t. This is just the other thing. The trick here is that by looking at this, we see that we have now this is, as I said, a row vector. We now multiply this here with the right part of it, which gives us again an expression of x a and xb minus mu, right? With these matrices here, sigma bb times sigma ba, and in the end, we'll have something that can be expressed as xa given xb times p of xb. This is the whole trick of it. Why is that? Because this part, where only b's appear, can be pulled out of the exponential, right? So again, this is a row vector. So what you do is you have this times the right part of it plus this times the right part of it. And because there's a plus sign in the exponential, we can pull this out and we have exponential of one times exponential of the others. So the plus turns into a times, right? Again, I'm not doing all the steps because it takes me too long here. For you, this is a good exercise to do that, right? You have this big exponential and you split this up into one exponential times the other exponential. And the second exponential only has b's inside. There's no a's anymore, which you can then express as just the probability of b. Right? So in general, we have a probability of the joint equals a probability of the conditional times the prior. And now we have these three exponentials, one here, one on the left side. And that means we have already directly an expression for the conditional. We just read this off, right? We just compare what's now this part where we just read this off. So the solution is this here. It's another Gaussian. This condition is another Gaussian with a certain mu and a certain sigma. And the mu and the sigma can be expressed just like that here. We just have to, like xa, we just take xa off and say, what's the rest? Well, the rest is mu a, right, plus sigma ab. Of course, we have to transpose this whole thing, right? This is a little tricky here. So this would be then, in the end, this is BA at the moment, but we have to transpose this whole thing because you have to write it in transpose again. That means we have times sigma AB times this transpose, it's the same because it's symmetric, times this transpose, right? XB minus mu B. That's right, just right there here. XB minus mu B, right? This is the mu thing, and the sigma, we know the sigma already. That's the Schur complement, right? We did that already. The sigma of the conditional is just the Schur complement of the whole matrix with respect to sigma BB, right? It's that thing here. This matrix is our inverse of the covariance matrix of the conditional, right? Covariance matrix of the conditional, the inverse of it is just this here. Okay? So what this all means is that Gaussians are very nice because everything is in closed form. It's a bit of math. You have to be like careful, compute a lot of stuff, but in the end, you don't really have to worry about how to compute all these things, right? It's all nicely done, right? Once you have this, you can then easily work with all the distributions, right? And you can easily find these marginless. So enough of math. Let's start with the definition of a Gaussian process. A Gaussian process is a collection of random variables, any finite number of which have a Gaussian distribution. We said this already, right? We have a given number of variables, can be infinite, right? This is explicitly here said in the definition. The number of random variables that we're talking about can be finite or infinite. And particularly if it's infinite, then it's interesting. So we define something of an infinite set of random variables, but we constrain it so that if we pick any subset, any finite subset of these infinite many variables, then this finite subset is jointly Gaussian distributed. The whole idea about this, or what this means, is that a GP is essentially a distribution over functions. Why is that? Well, because we are talking about things that are infinite. So we can think of, instead of having a vector of fixed length, of finite length, we have now mu vectors and sigma variances of infinite size. And we can interpret this as a function, right? We can interpret the mu. Usually we have a normal vector of finite length. Now we have a vector that could have infinite length, right? And this can be interpreted as a function. So it's an infinitely long vector. That means we have a mean function now instead of a mean vector. And we have also a covariance function, right? And again, same or equally, in the same case as we have standard Gaussian distributions, we only need these two things to define the Gaussian process, right? Whereas for the Gaussian distribution, for the finite distribution, we need a mean vector and a covariance matrix to fully specify the Gaussian distribution. Here we only need the mean function and the covariance function to specify the Gaussian process. Let's start with a small example. Here we have some artificial data set. The green line is some data where some ground truth data. It's a sinusoidal data source. Then from that data source, there are some samples, some blue circles here, and there's some Gaussian noise added to this data. And now what you can do is you can now try to find the Gaussian process that explains that data. And what comes out in this case here is this red curve, which is the mean function. And there's this light red area around the mean function, which is 2 sigma of the covariance matrix. So this is the 2 sigma covariance interval, right? So we have to think of this now as a function which is a sample from the Gaussian process. And the most likely sample is the mean function, right? This is the red line here. But if we sample very often from that, we will have other functions that are somehow or very often within the reddish area, right? We have things that are not exactly the mean, but very often we expect them to be very close to the mean, which is exactly the same concept as with Gaussian distributions, just now applied to functions. Okay, that's very nice all, but there's one big problem. How can we handle this infinity? How can we deal with infinitely long vectors? And the answer to that is because Gaussians are so nice, we can do that. And why is this? We can then simply think of this as an example of an infinite dimensional feature or a vector that is distributed as in a Gaussian process, right? So you have a vector, and this vector we can now split into a finite part and an infinite part. Right, so this very long vector, this very infinite dimensional vector, is now distributed according to a Gaussian process, where we have again an infinite dimensional vector here, and this matrix here is also infinite, right? So there's some finite part here, and there's some infinite part here. So there's infinitely many rows, columns, and rows. So it's a very, very big matrix, but we have a finite part and we have an infinite part. And the whole trick is that the Gaussians, if you compute the marginalization over this, so if you compute P of xf, which is defined as the joint where we marginalize out all the infinite things, right? This is just the definition of marginalization, where we average over all infinite parts of the GP. Then the theory says that this is exactly just the Gaussian where we only take the finite thing. So we have the finite mu and the finite sigma. So we don't have to worry about the infinite parts of the Gaussian process, right? There's also another way of saying this. If you ask finite questions, you get finite answers, right? That's the nice thing about it. So only for that reason we can use, we can deal with finite and infinite dimensional features or vectors. Let's go again to a simple example. We had already the Bayesian linear regression. So this is our formula from the Bayesian linear regression. We have some prior probability W here, which is our, so we can also interpret this as a regularization. What this means is that what we can do now is we can compute from our y function, we can now compute from that a mean function, right? By simply taking the expectation value of y. But of course we have to do the expectation over w. That means we pull in the expectation value. It doesn't affect our phi function here. And as we assume that the expectation of e over w is 0, this whole thing is 0. That means in this particular case here, our mean function is the 0 function. And that's what we very often use. And in most cases, if you use GPs, then you always assume that your mean function is 0. It doesn't really affect much of your training, right? It doesn't. Yes, so this is the predictive, the mean function of your predicted GP, right? So this is, if for a new x here, this is just what you expect on average, right? That kind of means that if you have no idea about w, your prior information about w is it's distributed around 0. So then that means that your predictions. Yes. So yeah. So if turn it the other way around, if you say that your mean function is the 0 function, then this equals the case that you say your prior is 0, right? You can equate that. You can say, if I use that as a reasonable prior for my parameters, then this is the same as using a mean function of 0. And the covariance function, we can also equally complete the covariance function between two data points, x1 and x2. So we have the prediction of these two data functions. And the same thing happens here. So we pull in the expectation, and we know the expectation of this already, which is just the covariance matrix of our prior. This is again a Gaussian here again. So this sigma p is our covariance matrix from our prior. So we just plug this in here, right? And in the normal case, what we assume here is this is a diagonal matrix where we just have one covariance value for all dimensions. That means we have just sigma times some I value here. So this is just a diagonal matrix here, right? This sigma p, right? And now any number of function values are now jointly Gaussian with 0 mean, right? And now we can also formulate that in more general form. We can say this whole thing here is nothing else than a kernel function again, right? So this is a specific kernel function. And now we can, of course, use other functions. So the GP is a more general form of describing this. Okay, and let's talk about covariance functions. They are very important. So there are many different covariance functions, but there's one which is used very often, which is this one here. It's the Gaussian, the squared exponential, the radius basis function. It has many names, but it's actually always the same, right? It has always some kind of factor before. There's the signal variance here called. It has a very important parameter which is called the length scale, yeah. And it has some noise variance in the end, so it adds some noise. This comes directly from the regularization here, right? So this is we had this already in the regression case. We just have plus some noise here. We'll see this later where this comes from. There's other possibilities. There's this example here, but it's not very often used, right? The most often used covariance function is this here. Okay. Now, one interesting thing I would like to also say is here. Now we have, if we define a GP, then we can do the same thing as we can do if we define a normal Gaussian. So if we have a normal Gaussian distribution, then we can use that distribution to sample points from the distribution. The same thing we can now with GPs. We can now sample functions from the GP. Right? This is very interesting. How do we do that? So every sample, again, will be now a function. First of all, what we do is we choose a number of input points. We usually call them with stars here. We compute now the covariance matrix K of these input points. And now we have an n-dimensional, an n-varied Gaussian, and we can now sample from that Gaussian, right? We're given, let's say we have zero mean, and we have some covariance matrix K. Now we sample from that Gaussian, and now we have x, y values, and we can just plot them, right? Again, we don't have a closed form of that function. We cannot really write down the function, but we have a mapping from x to y. We can say for every new data point, give me its likely output and its uncertainty about this output. It's this here, right? So if you sample from, for example, a squared exponential kernel, then we'll have these kind of samples here. These are just samples. Every function here is a sample from the GP. And here's the same, right? We sample from with a different kernel, but again, we simply have functions here as samples. Yeah. Let me do one more slide before the break. The most important thing to do with Gaussian processes is, of course, to do prediction. And the way we do prediction is completely, totally related to what we had here with the conditional. So the idea to do prediction with the Gaussian process is to first describe your the Gaussian process with the training data, and then add your test data into your vector and condition on your test data. So that means on the training data and some given test sample x. So what we have here is we have training data xn to x1 to xn. This is the given data. It's without stars. We have some test input, right? We can say we have a number of new data points. We'd like to find the function value that is assigned to a new test point. Yeah, this is exactly what we want to do, about why we do prediction. And we have these test outputs here, right? This is the ones that we would like to have, right? We would like to have a distribution over these test outputs. So now we write this again as a big joint Gaussian. We have all these y vectors. They are distributed in a Gaussian process where we assume we have zero mean, and we are given this covariance matrix. The lower left part of the covariance matrix is what we already have from the training data. But we can also now compute these parts here, because we are given this extra, right? And we simply add that to the big matrix, right? We have a big joint covariance matrix. And once we have that, we simply plug this into our formula for the conditional, and then we get it, right? Now for one example, a particular example, if there's only one test point, right? If we only take x1, then these parts here are particularly easy, because then this is a vector, and this is a vector, and this is a scalar, right? This is very easy. So the vector looks like this, right? This is again the kernel function applied to all the training data, with our new test point, which we call now x star or k star. And the scalar here is just the kernel function of the test point with itself, right? I'm not showing this here. Now we have everything in place to just compute the conditional distribution, right? Now we just condition on our data, x, y, and on our test point. This is training data, and this is test data. And what we get is another Gaussian, and the mu and the sigma of that Gaussian is simply our formulation for the conditional. We have seen what the conditional is. We just plug this in, and it's very easy because we have a zero mean Gaussian, and we have all the other things already given. So the mu function is just this here. The mu, the predictive mean, right? This is the mean of our predictive. This is again a scalar, right? We have only one data point. That means our distribution is a one-dimensional Gaussian with one value here, and this should be a sigma. This should be not a matrix, but this should be a scalar, right? Again, right? So we have a scalar here. This is a scalar, and again we see here a similar thing to here. So we have a dot product here with all given things, right? So this is also easy to compute. And again, if you look at this whole thing, it looks very much like the Schur complement. It's very similar to a Schur complement because just with this as a value instead of a matrix, but all the rest is again a Schur complement, right? Yeah. So now what we have is we have for any given new test feature point y star, we can now compute a mu and a sigma, which then defines us our so-called predictive distribution, right? And that's nice because now we not only have a most likely assignment of that new data point, but we also have an uncertainty about it. We can say, very likely, our new data point y equals to mu, which is, of course, our mean, our most likely value, but we also have an uncertainty measure. And this is just two examples how we can do that. So this is just sampling from a Gaussian process prior. We said this already, just without any data points. We just sample, and it can be any function. But if we condition on our training data, then the samples go all through data points, right? This is, again, we have, again, a Gaussian process. Now the only difference is that we condition on the training data. And then suddenly, all the functions that we have, they go through the data points. Okay, let's have a short break if there's no questions. Now I have also some sound. Okay. Again, so we have seen how we can sample from a Gaussian process prior, and from a predictive distribution, which is the posterior. You can say the conditional, where we condition on the training data, and we see that all the samples go through the data points. What we have implicitly assumed here is that we don't have any noise in the data. That means that every data point that we observe, we assume it's perfect, right? That means that every function that we sample from the GP goes directly through the data point, right? There's no variance around the data points. But usually we don't have that. Usually we have to assume some noisy observations, and it turns out that the formulation is then only very slightly different. There's not much difference here, as long as we assume that the noise is Gaussian. So what we do here is we introduce so-called latent functions f, and now the whole formulation is in terms of f. So now we have given noisy training outputs, given training data, right? This is x and y. This is again the same as before. Now just with a slight difference that y is some noisy variant, some noisy examples of f's. And the f's are the true functions that we don't know, right? That's the reason why they call them latent functions. We don't know the real value, the actual value that the function gives us. We only know y, which is a noisy version of f, right? And now the formulation is the same as before. We now have everything in terms of f. We say the predictive distribution of f star, which is the new function f. This is the true noise-free function value. We'd like to find the probability of the noise-free function value is now a Gaussian over f star with some mu star and sigma star, which is very similar to what we have here, right? So this wouldn't change much. The only difference is now that we have here f instead of this is the same here. Yeah, it should be the same formulation actually. Now we have seen that a very important thing here is to define the covariance matrix, the covariance function. The covariance function goes in here, right? Covariance function directly gives me a way to express the covariance matrix of our GP, right? And as I said already, the covariance function has a number of parameters, and this slide should show you just what happens if I change these parameters, right? You might think of, well, we wanted to get rid of parameters. That's the whole thing, the whole reason why we do this. We don't have a parametric model, but of course we assume some kind of covariance function, some kind of measure to find similarities between data points, and this function has parameters. So it's almost impossible to have any algorithm that goes without any parameters. But these parameters here are different than normal parameters. These parameters are called hyperparameters, because they only influence the prediction implicitly, right? There's no explicit model fitting where you just try to find parameters of your model. What you do is you assume some kind of covariance matrix, and the covariance matrix is computed from the covariance function, and that function has these parameters. But we can learn these functions from data. We'll see this these values from data. We see this later, how this works. This just shows you how what's the influence of them. So L, again, is the length scale, and sigma f and sigma n are the noise parameters. What this does here is, it shows you examples with different L's, right? So just look at the L function. What happens if you change the length scale? If the length scale is 1 for the same data, then your the mean function is the black curve here, looks like this here, right? If you reduce L, like if your length scale is smaller, then you see that the function is much more wiggly, we call it, right? So it's like much more, it tries to fit much more into the data points, right? You can interpret this as the influence of every data point is now less. So the range, or let's say the range of correlation between data points is smaller, right? This data point and this data point, they are, in the sense of this length scale, far from away from each other, right? And the data in between is more uncertain, because there's less influence of this data point to its neighbors. This is the way of interpreting it. This is why it's called length scale. Length scale tells you how far away from the data you have to be to still be correlated to that data point, right? And here, already after a few steps here, if you're not very far from the data, you are already decorrelated, right? So your uncertainty is very high. You don't know what you have here, and the mean function has a higher variance there, right? Whereas if you increase the length scale, then the influence of the data points increases as well. So there, things are much more correlated with each other, right? This covariance function should be less sparse, and this is more sparse, right? Okay, we can of course set these parameters. And this is again our covariance function. We can also extend that covariance function to m dimensions. So we can have a value here, a matrix here again. And for different cases of this matrix M, we have different types of covariance functions. So this is just to show you that there might be different ways of constraining the covariance functions, right? Instead of having one length scale for all feature dimensions, you could have for every feature dimension have a different length scale. So this would be the same length scale for both feature dimensions. So we have two feature dimensions here, and this shows you the sampled output, right? The GP output here. If you use a diagonal matrix where you have different values for every feature dimension, then you see that there's a higher correlation between data points in this direction than there's in this direction, right? So it's smoother along the x2 axis than it's along the x1 axis. Yeah, because the length scale is higher. Right? This is just a length scale in x2, and this is the length scale in x1. So in this direction, there's less influence of the data points with each other. And then you can also even extend that to matrix forms here. Here you have along the 1 minus 1 direction, you have a higher, a lower correlation between the points, and along the orthogonal of that, you have a stronger correlation between the data points. Okay, this just shows you one slide about how to implement all that. There's more to say about this, but I'm not doing this in more detail. The reason why I'm showing this is to show you that it's actually very simple to implement that. There's a little trick here that you use, which is simply that instead of inverting this big matrix, this K matrix, we use, or for doing that, to do that, we use the Cholesky decomposition, right? The reason for Cholesky is that it's numerically more stable, and it has other advantages because we can then use also that in an incremental step. There's an incremental version of the GP where you can then pre-compute the L Cholesky matrix and then add new data points to it and then only do rank 1 updates to this Cholesky matrix. But it's not a topic of this class today, but in general, this is the way of doing it, right? So you first compute the whole big matrix, of course, right? You have all the training data points, x and y. First, you compute for every pair, xi, xj, in your training data, you compute this big matrix, right? Of course, you only have to do half of the matrix because it's a matrix. You don't have to do this for all pairs, just for the half of it. But then once you have the covariance matrix, you compute the Cholesky of this thing here, right? This is just comes directly out of the equation that we had before. We could also have this already computed in the covariance matrix. So this is actually already the result of our kernel function, right? Here we have our noise parameter here in the kernel function, right? Okay. Then what we do is we pre-compute the inverse of k times y, and we do this with backward and forward substitution of L, right? This just makes things more efficient and numerically more stable. And then in the test phase, we get a new x star. We compute for the new x star, we compute k star, which is simply the vector of all correlations with x star to all the training points, right? This k star needs to be computed, and the most likely output, which is our mean, predictive mean, is simply the dot product of alpha with this vector. So this is very efficient, right? The only thing you do is once we have alpha given from the training phase, we only need to compare the new data point to all the training data points and do a dot product with alpha, and then we get a most likely value for the output of x star, which is f star, right? But of course, in addition to that, we can also now compute a variance, right? An uncertainty measure. How certain are we? Or we compute now from the formula as above, the Schur complement, which is nothing else than, given the Cholesky decomposition, we just do L forward substitution at k star, right? This is one part of it, and now we do v transpose v, which then transforms into our formula k star transpose times k minus 1, right, where k is the covariance matrix, times k star, right? This is just exactly what we had before, now expressed with Cholesky decompositions, right? And this is, of course, our self-similarity, we can say that, right? This is how the new test point is correlated to itself. And again, this thing here is the Schur complement. And then what we also can do, this is what we see later here, this is the marginal distribution. We'll see this in the next slide, where we do this. Yeah, because what we also need to do is we need to compute the probability of y given x, where we marginalize out all the latent variables. The reason why we do this is that this is all given. We know y, we know x from training data. This is just all the training data. But what we don't know is the hyperparameters. So this expression here only depends on the hyperparameters. And the nice thing about this is that this is, again, all Gaussian. So this is a Gaussian, this is a Gaussian. We know all these Gaussians here. We know that this is our noise, right? For a latent function, given latent function value f, our likely output is, or y is distributed as a Gaussian, and this Gaussian is has a diagonal matrix, which then means that we can multiply that, we can express it as a product over one-dimensional Gaussians, right? This is just the product over all y's given fi's, where every of these single Gaussians has just the same variance vector here, variance value here, right? This is just the product over these. Which assumes that all the training data points are independent, conditionally independent, right? But that's a reasonable assumption. So this is a Gaussian, this is a Gaussian, and the result is this here. The trick here is to use the formulation for the linear Gaussian case. So we have one Gaussian that depends linearly on a term of this thing here. So here we have f, right? And here we have f. So if this is the case, then we can plug this into a formula that we have for the linear Gaussian case. We'll see this also in the next slide. And then we can directly compute the Gaussian for this thing here. So for the particular case we have here, this is 0. Because this is 0, this will be also, the marginal will be also 0. And the covariance matrix of this marginal is just the sum of our covariance matrices here and here. Right? This is our diagonal matrix. Yeah, sigma y squared times I. This is a diagonal matrix with sigma y on the diagonal. Right? This is basically the product of all these Gaussians here. And the covariance matrix of this one is known already from this is K, which we know from the Gaussian process. So we simply have to add these two matrices, and we can compute the marginal likelihood here. Right? Now again, we are kind of hiding the hyperparameters here, right? The hyperparameters, they go in here, right? We need them to be able to compute k. Now what we do is, we take the logarithm of that, derive with respect to the hyperparameters, set to 0, and solve. Right? That's the idea to do. This is the training step of the GP. Right? To find good hyperparameters, we simply take this expression here, logarithm of it, which makes things easier because then we only have to compute. We don't have to do this exponential stuff anymore. We just look at what's in the exponent. We derive this expression with respect to the parameters, hyperparameters, set this to 0, and find the optimal hyperparameters that explain our training data. Right? This is just a training step of GP. And this is what comes out. The problem is that this optimization here is not convex, so we will not have a unique optimal solution. We might have different kind of solutions here. This is one example where there's two solutions, and this just shows the two-dimensional space. This is the length scale, and this is this one noise parameter here. And you can see you can have one length scale with these are the two optima here of the optimization technique, and these are the corresponding functions here. So with the I think this is the low length scale with low noise which should be this here, right? So there's a lower length scale, so this curve is much more wiggly here, and with the higher length scale we have this here. And it's sometimes not so easy to understand, to find the best one, right? It's not clear which one of these should be better, right? Those are both local optima. Another thing we can do is, I said this already, instead of having one length scale for all feature dimensions, we can have for each feature dimension a different length scale, right? So this is now a sum over all feature dimensions, right? And now for every dimension in feature space, we have a different length scale. So that means we have now, instead of 3 parameters or 2 parameters, we have this one parameter, the sigma f, plus d parameters, right? So we have to estimate many more parameters now. But by doing that, we can find relevant feature dimensions. So this is an example where we have three feature dimensions, or 2 feature dimensions actually, and we try to fit 3 parameters in here, right? We say feature dimensions should be, well, the given feature dimensions are 3, but one feature dimension is not relevant at all. So after, this is some kind of iterative process that is doing here. I'm not going to the details here, but if we do that optimization technique, then we can find out sometimes that some feature dimensions are more relevant than others, right? And if this eta 3 here goes very small, then we can say that this feature dimension doesn't give me much information, right? It's not a very relevant feature, right? Implicitly, this comes from the estimation technique. Yeah, that's very nice to do, right? I can show the algorithm a lot of feature dimensions and try to fit parameters in there, but the algorithm will tell me I'm only looking at these 2 feature dimensions because the other one is not very relevant. Okay, so far the regression. Let's go into classification. Classification is probably, yeah, we have seen this very often. We need classification techniques, but we also thought, or have you seen already, is that we can use regression for classification. And the same idea we do now for the GP, right? We try to find an expression to find a classification algorithm where we base that on what we see already from regression. And the idea to do that is, first in regression here we have y as a, the only difference between regression and classification is that y in one case is a real value and in the other case it's just a binary value, right? So y can be just -1 + 1. And the only step that we do now between regression and classification is that we apply a function called a sigma function. This sigma function here is applied to our prediction of f, and sigma is simply a function that maps the entire real numbers into an interval of 0 and 1. So every value on the real axis is mapped into the interval between 0 and 1, right? And we'll see examples of sigma functions here. And we assume that this is symmetric. That means that sigma of minus z equals 1 minus sigma z. Then we can directly say that the probability of y of given x is sigma of y times f, right? We can express this whole thing just as that here, if we know that sigma is symmetric. Now, this is one typical example of sigmoid function. This is a so-called logistic sigmoid function, but we have other sigmoid functions. And this is what happens with our Gaussian process if we apply a sigma function. This is just one sample, again, a sampled function from the Gaussian process. You see the values here, they can vary between 8 and -5 or something like that, right? There's no restriction on where this function, the range of this function is. It can be any number. But now if I apply a sigmoid function to that function, then things are squashed into the interval between 0 and 1. And now we can interpret this as probabilities, of class probabilities. Now we can say everything which is very close to 1 corresponds to a probability of almost 1 to be class. And everything very close to 0 is the probability of not being class. Right? This is just the way of converting a regression algorithm into a classification algorithm. And another sigmoid function is the so-called cumulative Gaussian. So we have two sigmoid functions. This is the reason why they're called sigmoids, because they look like an S, right? The S-shaped functions. This is one S-shaped function, this is the other S-shaped function. And you can see any value on the real axis is mapped either to 0 or to 1 or somewhere in between. Right? And now we can use directly that value and interpret it as a probability. Say, what's the probability of being class? Well, it's a sigmoid of the function that we get from the GP. Right? And the way to express that is the same as before. We do the same as we did with the noise function, with the noisy parameters. We treat f as so-called latent variables, right? We say our regressor gives us a function value that we don't know, right? It's a latent function value. But from that function value, we can then compute a label by simply applying our sigmoid function, right? So, and the trick now is to marginalize out over all latent functions. And I'll show you in a second how this works. What we want to do is, we want to compute the predictive probability of class 1 given the training data and the test input, right? This is again the same as before, right? We have here, what's the probability of being class given our training data, x, y, and given our test input, x star. We can now express that as a marginalization over all f stars, right? This is, again, the marginalization thing, where we just say, this is our likelihood, right? We assume that we know f star, right? We know the most likely function value for x star, right? I give the GP, I train the GP, I show it an x star value, and I would like to find the most likely f star value, or any f star value, right? If I know that, then I can easily compute y star, because this is our noise model, this is our sigma function, right? This is how likely is it to have label given our function? Well, this is just a sigma function of f, right? And this thing here is our predictive distribution that we had before from the GP, right? This again can be again written as a marginalization step, where we have this here. This is now exactly the same formulation as before with regression. Now we are again in regression land, right? Now we have x and f given from the training data. We know everything now. And we give, again, x star. And we can now predict this f star here, right? This is, again, a nice Gaussian thing here, times this prior here. And this prior, we have to look into more detail in this prior. What is this? Of course, this is defined. This is what the Gaussian process defines, but we have a slight problem here, or a slight difference here. This f here can now express as a Bayes rule, right? This Bayes rule is, as I said, a very important rule here. We turn things around here, right? We say f given x and y is just y given f times f given x divided by the normalizer. We have a prior, we have a likelihood, and we have the normalizer. Again here, this likelihood, we know this, right? We know all the terms, basically. We know this prior, which is our Gaussian process, right? The Gaussian process just tells us, for given input data, what's the most likely latent functions. This we know from the sigmoid function, right? This is, again, now the sigmoid function applied to the training data, not to the test data, right? This is for the test data, this is for the training data. But it's the same, right? We just assume that once we're given a latent function value f, we know what's the most likely value, label y. Right, and we normalize that with this here. And the whole thing, ideally, should be again a Gaussian, right? We're never really computing this value. We're always dealing with distributions, right? So again, what we compute here is a mean and the covariance matrix. So this whole thing should be Gaussian. The problem is that this sigmoid function is not a Gaussian, which means that this whole expression cannot be written in closed form anymore. Now we have the little problem, right? In regression, we had Gaussian noise here, right? From a given function value to a noisy observation, we assume this Gaussian, then the posterior of that whole thing is again Gaussian in all closed form. But now this is not Gaussian anymore because we have a sigmoid function here. Before we look into that, we just look at some examples, or one simple example here. The red data points, I sampled that this is a two-class training data set, right? We have -1s and +1s here. And now if we fit a Gaussian process into that, then we find a mean function, which is the green one. And you see that this green function here, this is the most likely latent function. This is the f, right? It's basically the f, or let's say it's the mean function of this distribution here, right? This is a Gaussian again with a mean function and a covariance function, and the mean function is the most likely function of the training data, which is the green function. And we see that the function, of course, has values that are smaller than -1 and bigger than plus and 2, right? The values of this function can be arbitrary, can be very, very high range, right? But now what we do is we use that function and apply the sigmoid to it, and the light blue one here is the sigmoid function. And now we have probabilities. Now we can say probability of class 1 is 0 here, and probability of class 1 is 1 here. And in between, we have some kind of intermediate probability, right? So you can probably threshold this whole thing at 0.5 and say, what's the probability of being class? Well, all these points here are more likely to be class than these points, right? This is the whole idea of doing classification with a regressor. Now, let's go back to the problem. We had this expression here, and to compute that, we have the problem that the likelihood term, this term here, is not a Gaussian. And that means that we cannot compute this whole thing in closed form, but there are now ways to do that with approximations. And one common approximation is the so-called Laplace approximation. Another one which works even better is the so-called expectation propagation algorithm. And there's other methods called variational methods. I'm only giving a very quick introduction to Laplace. I'm not saying how this works. It's all based on the second order Taylor expansion of this posterior here, right? So you approximate that with a Gaussian. Yeah, Q is now a real Gaussian where you have a mu and a sigma again, and you compute this mu and sigma with a Newton step, a Newton method where you have a gradient and a Hessian matrix, right? The Hessian matrix can be computed as this here, and this W here is a diagonal matrix. Again, I'm not going into the details. This is just the rough idea, right? It's a very common way of doing that, approximating your this distribution, whatever it is, with a Gaussian distribution, and this is the way it looks like. So this is one example. The yellow-shaped area here. This is the posterior that we'd like to approximate, which you see is not Gaussian, right? It's something similar to a Gaussian, but it's not a Gaussian. And Laplace, what it does is it finds the mode, right, which is the same as a mean for the Gaussian, which is the maximum of our distribution that we'd like to approximate, the yellow one, and around that we compute the Hessian, right, at this position, right? This is basically the rough idea how Laplace works, right? You can see it's a not so bad approximation, but there are better ones, and we'll have another algorithm that does this much better in a later class. But this is, as I said, a very common way of doing that. Now, if we have our Laplace approximation, we can now do predictions. Again, this is our formulation for the predictive distribution here for the F star, right? So again, this is, I just copied that from above. We have now this as a Gaussian, right? We have approximated this with a Gaussian. We can now plug into our formula again with a linear, Gaussian linear model here, right? This is a Gaussian that depends linearly on something on F, right? Which comes from here. So this part here is just directly the regression part. We get this from above, So we get our formulation from above. This is the mu and sigma of our what the regressor says us, right? This is just the same formula as before. You see here, this is again the Schur complement, and this is linear in f, which means that we can now apply our rule for the linear Gaussian case. So this is just again the general formulation of that. I'm not going to this again. This is just the same formulation as we had already. The essence of it is that we can write everything again as enclosed form with Gaussians. So the solution is that we have a mean and a variance here, and that means we have this distribution given now, right? Right. This is this thing here, right? We now know this Gaussian distribution. We know now mu star and sigma star, right? It's this and this. Now the only thing that remain is we have to now marginalize out f star again, and this can be done in closed form if we have given a certain sigmoid function. For the standard sigmoid function for the cumulative Gaussian, we can't do this in closed form. But if we assume another sigmoid function, for example, the logistic, the cumulative Gaussian, then we can do this in closed form, right? That's all I say about this, right? That's the reason why sometimes you choose different sigmoid functions, because then things are very simple. And this is just a simple example how we do this. This is a two-class problem, and with red and blue classes here. And the green line is the optimal decision boundary, right? This is from ground truth. We know this from ground truth. And the black line is the one that the GP classifier gives us. And you can see it's very, very close to the optimal one. And this you see, this is just a colored version of this space here, where you see this is all blue and this is all red. And in the mean and like in between, we have uncertainties here. One last slide about GPs. There's a number of properties, good properties and bad properties. The biggest benefit of the GP is that it gives a so-called well-calibrated estimate of the uncertainty. That means the prediction is based on marginalization over all possible models, not a particular one. For example, for support vector machines, we fit one very best fitting hyperplane to the data. But the GP does not do that. GP does a marginalization over all latent functions, where every latent function is a possible model. You can interpret it as a model. And by doing that, it gives us a much better estimate of the uncertainty, right? So what that means is that if the Gaussian process gives me a label and gives me an uncertainty, then very often when it's uncertain, I can kind of can assume that it's wrong. So the correlation between wrong classification and uncertain classification is much higher for the GP than for other training algorithms, right? Which is very nice, because then I can improve, for example, classification by just removing all the uncertain labels, right? Where with support vector machines, I can't do that. However, the biggest disadvantage of the GP is that it's very inefficient, right? If it takes, for a few data points, it requires a lot of memory and it requires a lot of time. But there are techniques that can deal with that. So there's a sparse version of the GP, which I'm not talking about. The idea of the IVM, the informative vector machine, is just the same as for the SVM, that instead of using all the training data points, you just use a subset of it, which are very informative. It happens to be that these data points are very close to the border, which you can then interpret as kind of support vectors. This is just a note that there are efficient versions of the GP. Yeah, and to summarize the whole lecture of today, a GP is a normal distribution over functions. To specify a GP, we need a covariance function and a mean function. Very often, mean function is a zero function. For regression, we can compute the predictive distribution in closed form. That's easy to do. It's all Gaussian. We can all do this in closed form. For classification, we need a sigmoid function that squashes our latent function into 0, 1. And the problem with that is we can't do this in closed form anymore, but we can do this by approximating the latent posterior with a Gaussian, right? And if you want to see more on Gaussian processes, there's a very good video lecture on that by Carl Rasmussen. Thank you very much.